Today we're going to talk about a three-dimensional coordinate system. This is the beginning of chapter 12, first section. We've seen two-dimension already. If you have x and y coordinate, normally we have the two axes, the plane format. We have x and y axis, and any point in the space could be shown by the two coordinates, the corresponding x coordinate and y value. So here, let's say y1, x1, you'll have x1 and y1. For example, the point 3 and 4 would be value of 3 for x and 4 for y. So this would be the point corresponding to 3 and 4. We can extend the same idea to three-dimension. For three-dimension, drawing is a bit difficult. So here, I already have this picture. This is our corresponding x-axis. This is the corresponding y-axis. So this is the plane that we have in 2D. The same picture that we see here is that this gray plane. But we have another orthogonal axis, which is has a 90-degree angle with both y and x-axis. And x and y already have a 90-degree angle. So all these three axes are orthogonal to each other. You can look at the corner of a wall, and the three axes would be along each direction. So this is our z-axis. It's important that you keep this orientation of x, y, and z in the manner that if you put your hand along the x-axis, if your finger pointing along the x-axis, and if you curl your finger along the y, then your thumb should be along the z-axis. This orientation matters, so changing y and x might be causing some problems. So we normally have x, y, and z. Okay, so if you have a point in this space, for example, the point 4, 2, and let's say y value of 2 as well. So you have to go up 2 units. But it's difficult to see how much so this must be exactly along this y value of 2. So there is a point here where the x is 4, y is 2, and z is 2 as well. How do we show it? We say x is 4, y is 2, and z is 2. So the format for the three-dimensional point would be the three-tuple x, y, and z. This is the orientation or the points. So any point in 3D, this is point x, y, z in 3D. Okay, similarly, if this is the direction x positive, on the other side you would have negative x. If y is in this direction positive, then on the other side would be negative, and so on. Z is going above, and below would be negative numbers. Okay, let me erase some of these arrows so we have a more clear form in 3D. Okay. So normally you don't have this axis. So if you're trying to plot something, you should draw this three orthogonal-ish and say this is x, that is y, this is z. So if I want to show, for example, they say show point 1, 0, 2, you should say, okay, 1 for x, 0 for y, so there is no movement along y, so you have one movement here, no movement along y, and z2, so you go up 2 units, parallel to z. So this would be the point. 2 units here, 1 unit there. So if your y value is 0, what you notice is that you're going to be in the x and z plane, because the y value is 0. It means you're not going to have any movement along the y. Everything would be in the xz plane. It's kind of difficult again to see it, but I have an example later on we'll notice. It's better through that. Okay, surfaces. Surfaces are a bunch of points that satisfy a certain equality. Like if you had graphs of x squared, this would have been a y equal to x squared in 2D. This would have been a parabola, which means there are a bunch of points that they all satisfy this property, that if you pick the x coordinate, for example 2, the y value would be 4, satisfies this equation, x squared equals y. Surfaces have the same idea. There are a bunch of points that satisfy a certain equation. For example, our first example is x equal to 2. And we want to draw this surface. It's not always easy to draw, but some cases are easier. So here, this is in 3 dimension. If they don't say 3 dimension, x equal to 2 by itself could mean in 2 dimension could mean only y value is whatever, so x equal to 2. This would mean x equal to 2 in 2 dimension. But in 3 dimension, we have z and y are independent. That means there is no restriction on z and y. X must be always 2. How does it look like? Here I already plotted this so you can see it. It means x must be always 2. Doesn't matter where the point is. If you look at the x values here, they're all 2. Every x value is 2, but y could be different, as well as if you pick a point up here, z is, for example, 4, somewhere here, y is maybe -3, but the x value is always 2. This is so the plane that goes through the point x equal to 2 and parallel to the y value and y-axis and z-axis, that would be correspond to this surface x equal to 2. Here, this is one way to see it, and another way is if you rotate it a bit around. This is the same plane, x equal to 2. This is the x-axis, y-axis, and z-axis. And the same, I just rotated a bit so you guys can see. Sorry, this green line is y-axis, and here is z-axis. There's a website that you can go and try to plot GeoGebra or something, GeoGebra. You can plot 3D in this website. If it's not clear for yourself to draw it, you can go there and type in the equation. For example, type in equation x equal to 2 and change. Normally they start from 2D, but you have the option to pick 3 dimension. Then they will plot this picture. You can rotate it around and see a clearer picture of what they see. Okay, so for example, if you want to graph z equal to 3, how does that look like? So drawing, normally I don't ask you to draw, but it's a good idea to see z equal to 3. Here is z equal to 3. So any point with a z value of 3, maybe somewhere here, somewhere on the other side, all these points that have z value correspond to 3. If the z value is always 3. These points, if you look at them, they're going to be in a plane passing through the z value of 3. They all pass through these points. Okay, so this plane, z equal to 3, is parallel to the base plane, the xy plane. Okay, similar to the x equal to 2, which was parallel to the zy plane. Because there is no restriction on x and y. X and y could be whatever, but z must be always 3. And for y equal to 0, what does y equal to 0 look like? Y equal to 0 would be where y is 0, everything else is optional. You can pick any other point for x and y, for x and z. That means you have to have the plane that only depends on y value of 0. So y value of 0, origin has this point y is 0. The same as if I pick this point, y value is 0, there's no movement along the y. This point has no movement. Same, all these points. So what is this plane? The plane that goes through the x and z axis. Imagine the plane that is cutting through the x and z axis. So for example, in this plane here, going through all this. And it should go below as well. Okay. Again, drawing is difficult. Maybe use the GeoGebra. Try it out to see how it looks like. So this is y, x, and z. So y equal to 0 is basically the xz plane. That means the plane that contains both x and y axis, x and z axis. The same as if I would have said x equal to 0. This would have been the plane passing through the y and z axis. containing these two. And the same with z equal to 0 would be our x, y plane. Okay, so this is not very difficult. The problem is with the graphing, drawing of it. How about this one? X squared plus y squared equal to 1, and they give you z equal to 3. First, let's graph each one separately. The z equal to 3 must be the easy one. We already looked at that. Z equal to 3. Z equal to 3 was this parallel plane to the xy, it passes through 3. Again, I used the GeoGebra, so here is the z equal to 3. This purple one is the z equal to 3. But what is x squared plus y squared? If you remember in 2 dimension, x squared plus y squared equal to 1 was a circle of a radius 1. Radius 1. This point is -1, here is 1, and 1, and so on. So if you look at the equation, it is independent of the z value. That means there are a bunch of circles with the radius of 1 on the xy plane. So here is one of them. Sorry about this. And I see the next one would be somewhere here, and so on. All these circles are stacked on top of each other independent of what the z is. So they're a bunch of circles. And if you put them next to each other, on top of each other, what you get is basically this cylinder that goes on forever on either side. So if they ask you to graph both of these two at the same time, it would mean the intersection of these two. So the cylinder intersecting with this z equal to 3 plane, what you get is this picture. Again, you can always draw this through GeoGebra. So what you get is basically this circle. It's not a solid circle, so it's like it's basically empty. So what you notice is in 3 dimension, at the end, what you have is z equal to 3 and a circle with the radius 1 around z equal to 3 in the plane of z equal to 3. So this has a radius 1. This is basically our graph. I should draw it with a different color. Sorry. There we go. And this is a 3. This is correspond to exactly this circle. Okay. If you notice that one of the equation is the independent of variable, try to draw it first. If this is x and y, try to draw it into xy plane. Then just extend it through the same thing. If it was x and z, try to draw it in the xz plane, then it would be if it was x squared plus z squared equal to 1, this would have been a circle in the xz plane. That means you would have had a circle something like this. And then extend this circle along the y. So you would get a cylinder along the y. Bunch of circles next to each other. Again, it's tough to draw, so try to use the GeoGebra to see how this plots and surfaces look like. Okay, now what we focus on is the distance formula for the moment, because we will need it later on. We know already the distance formula in 2D. What is the distance formula in 2D? It was if you have 2 points and you're going to find out the distance between these 2 points. Let's say point 1 has the coordinate x1 and y1, point 2 has the coordinate x2 and y2. The distance between these two, you would have used a Pythagorean identity and say, okay, this length is x2 minus x1, sorry, x1 minus x2 or x2 minus x1. Let's change these order. y1, x2, it doesn't really make any difference. x2 minus x1, and here this length is y2 minus y1. Then what would be the length? You use the Pythagorean identity, say x2 minus x1 squared plus y2 minus y1 squared must be equal to the distance between these two. So let's call it distance squared. So what would be the distance? Distance would be basically the square root of this. This would have been in 2 dimensions, distance between 2 points. In 3 dimensions, it's exactly the same. It's hard to see that for example, if you have 2 points P1 and P2 with the coordinates are x1, x2, x1, y1 and z1, and x2, y2 and z2, they are not aligned in the same plane. They might be somewhere opposite across the, maybe if you look at this point and say it has some x and y and z, the other point may have all different x, y, and z values. So you can look at them as being across a box. And how do you calculate the distance from one corner to the other? Would be first you look at this triangle, and then you look at the other triangle. From the green one, you can find this length, because the green is basically the difference, for example, between the y2 minus y1, and here would be the difference between x2 minus x1. So you can figure out this length, which is basically that square root of y2 minus y1 squared. Sorry, let me be a bit organized. So this length would have been square root of y2 minus y1 squared plus x2 minus x1 squared. That would be this distance. And then this length, this height, would be exactly the same as the difference in the z's, c2 minus z1. So what our distance, the distance across the two, sorry about that, the distance across the two corners of the box, it would be this length squared plus this length squared, and take the square root. It's the same Pythagorean identity. So if you do that, what you end up with is the distance between the 2 points P1 and P2. This absolute value shows the length. The length between the 2 points P1 and P2 is basically x2 minus x1 squared, y2 minus 1 squared, z2 minus z1 squared. It's just the same idea as the 2 dimensions. You add those numbers and take the square root. This would be the distance one. Which means we can find the equation of a sphere. We use the 2 dimension to find the equation of a circle. For the sphere, if you know any points, if you have a sphere is a circle in 3 dimensions, which would give us something like this. Imagine a ball with the center somewhere here. Let's pick the center to be the origin for the moment. The distance between the origin and any point, this distance, always a fixed value. And what is that fixed value? Is the radius. So that means that equation of a circle would be any point you pick minus the origin has a distance of r. The difference between this point and the origin would be always a fixed value of r. So if you pick the center to be h, k, and l, so if you have a circle with the center h, k, and l, the difference between the x, y, and z from the center, and if you square it, take a square root from that, then that distance would be a fixed value of r. Just to get rid of the square root, we will square both sides. So the equation of a circle is basically, let me erase this, y, x minus the corresponding center value of the sphere, x value of the center, and y minus the corresponding y value of the center, and so on. All these squared added up together would be the radius squared. For our 2 dimension, it was x minus h squared plus y minus k squared equals radius squared. This was in 2 dimension for the circle, 2D circle. 3D circle would be basically a sphere. And if you notice, we did an example above here. This was a circle with the radius 1 and center 0, 0. X minus 0 squared, y minus 0 squared equals to 1 squared, which gave us this circle of radius 1. So here is a plot of a sphere, maybe multiple spheres. And the question is, what is the region represented by this equation? At first, you look at the inequality and it looks confusing, but let's ignore the inequality and just look at 1 equal to x squared plus y squared plus z squared. If you ask yourself, what is this representing? If it's complicated, and by putting 1 here, put the 1 on the other side, look at it this way. What you notice is exactly this equation, which is the equation of the sphere, where the centers are picked to be 0, h, k, and l to be 0, so therefore you have x minus 0, which is simply x. You have x squared, z squared, and y squared. And on the other side, you have radius of 1. So this is basically a sphere with the center 0, center origin, and radius 1. And if you look at the other side, if you set that equal to 9, what we get is x squared plus y squared equals z squared, plus z squared there we go, plus z squared equals to 9. 9 is basically the same as 3 squared. So the radius is here is a sphere with center origin, radius 3. Okay, but you have inequalities. That means any sphere in between, where the radius is between 1 and 3, this is not 1 and 9, the radius is 1 and 3. Any sphere between that is acceptable. All those points are acceptable. So the region between this sphere, the red sphere with the radius 1, and the sphere of radius 3, actually what I've plotted here is on 3, it's not on 4. This is, if you'll notice, this is the sphere. Don't assume that this goes through 4. That's the lower part, and visualization kind of is confusing, but we have a sphere of radius 3. And here you have a sphere of radius 1. Okay, in each direction this is radius 1. Okay, so what we have is all the area, all the volume in between these two spheres, plus the spheres because you have the equality option. If you didn't have the equality here, for example, then that boundary of the red sphere would not be acceptable. But since we have the equality, that means all this area volume between the two spheres is what we're looking at. This represents that volume. Okay, if, for example, if they would have said x minus 2 squared plus z squared minus y, plus y minus 3 squared equal to, let's say, minus 5 equal to 0, and they ask you what is the radius and center of this sphere, then this radius, the center of the sphere would be, normally they use C to show the center, would be 2 for x, not 0 for z, but 3 for y first, then 0 for z. If it was plus here, you should say minus 3, right? And the radius, what is the radius? You can move this constant to the other side and say, okay, this basically is the same as saying equal to 5. Radius is not 5, but square root of 5. This is supposed to be r squared, so the radius would be square root of 5. Okay, and if it was, instead of 5, if it was 0, what does that represent? The radius 0. Radius 0 means you just have a point. Where is that point? That point is exactly at the center. 2, negative 3, and 0. 2, 1, 2, negative 3 along the y. 1, 2, 3, here, and z 0. So that is the point with the radius 0. If the radius was square root of 5, then you would have this sphere of somehow. Just imagine you have a sphere. This is not even close in terms of graphing. Okay, let me not spend too much time on this. Okay, so you find the center first, then you look at the radius and you can graph it. It's not that important, the graphing is just the understanding that matters. Okay, So this is the first section of this chapter 12. We're going to continue chapter 12 by vectors next time.